There is said to be a $14 bucket of raw industrial powder sitting on the lowest shelf of a local hardware store, described as something capable of disrupting a multi-billion-dollar digital surveillance structure that is claimed to be mapping the interior of private homes. It is suggested that there is a strong interest in keeping its existence quiet, and that it should not be mixed into exterior paint. A clear statement is made about what is supposedly occurring at this moment while a person sits inside their home. A continuous flow of 5 GHz millimeter wave radiation is described as passing through exterior walls made of drywall. This is said to originate from smart meters attached to street infrastructure, cellular towers located roughly 2 miles away, and mesh network devices installed by neighbors inside their homes. It is framed as more than simple background connectivity used for fast data transfer. It is instead characterized as an advanced sensing grid operating in an active scanning mode. According to this description, every time these high-frequency waves encounter solid objects inside a house, the signals break apart. They are said to interact with items such as refrigerators, metal safes, bathtubs made of cast iron, and even the water content within a human body moving through a hallway. Upon contact, the signals are described as reflecting back and forming extremely small echo patterns. A reference is made to a concept attributed to a joint electrical engineering group from the Massachusetts Institute of Technology and a Silicon Valley spatial data company in the year 2018. It is claimed that by collecting these returning micro-reflections, it becomes possible to construct a precise, three-dimensional digital representation of a home interior at millimeter-level detail. This includes full floor layouts, identification of load-bearing walls, and observation of real-time human movement through interior spaces, even through solid building materials. The description compares this idea to the function of a stud finder. A standard stud finder is said to send a small electrical field into a wall and measure return density changes to locate wooden beams. This concept is then expanded by a factor of 10 million, suggesting a coordinated environment where routers, 5G nodes, and delivery drones act together as a large-scale scanning system continuously mapping residential interiors. In this portrayal, modern building materials such as fiberglass insulation, thin vinyl siding, and standard exterior paint are described as offering no meaningful resistance to these signals. From this perspective, the house is portrayed as fully transparent to such sensing systems. A proposed countermeasure is introduced in the form of a physical material described as a carbon-based isotope mixture. It is claimed that when approximately 12 ounces of this material is suspended in 1 gallon of exterior acrylic paint and applied to a house surface, it changes the microscopic structure of the coating after curing. This is described as transforming the exterior into a signal-absorbing layer that prevents reflections from returning. Under this claim, incoming signals would be absorbed rather than reflected, causing the supposed digital mapping of the home to disappear from remote systems. The house would effectively become invisible within the described network. The reasoning then shifts toward economic motivation. It questions why large corporate systems would be interested in the internal layout of private homes, and then answers that the interest is not personal but data-driven. The focus is placed on the value of behavioral and structural information, extracted from movement patterns inside residences. The existence of a large spatial data brokerage market is described, valued at approximately $412 billion. It is portrayed as an unseen economy operating beneath major technology and telecommunications industries. In this view, physical movement data inside homes is treated as a tradable asset. Smart meters are described as devices that do more than measure electricity consumption. They are said to identify electromagnetic signatures of household appliances and track their positions within a home using mesh network interactions. Opening a smart refrigerator is mentioned as an example of an event that can be detected and spatially mapped. The narrative continues by describing how movement patterns are used to build behavioral profiles. It claims systems can infer sleep arrangements within a household, detect nighttime movement patterns, and associate them with targeted advertising models. It also states that dense metal objects, such as gun safes, appear as voids in signal-based mapping systems. Each reflection of the 5 GHz wave is described as being converted into data points that are sold in large-scale automated transactions. This is compared to a hidden real estate market where interior home space is treated as a product. The explanation extends into insurance systems. It claims insurance companies purchase this spatial data and adjust premiums based on inferred household characteristics. Examples include increased rates when expensive electronics are detected in concentrated areas or when certain security structures are absent from entry points. The narrative suggests these adjustments occur without direct notification, framed as automated financial systems driven by data analysis rather than individual decision makers. It then attributes regulatory and economic influence to telecommunications infrastructure development. It describes lobbying efforts toward the Federal Communications Commission that allegedly enabled wider use of 5 GHz and 6 GHz frequency ranges. This expansion is presented as enabling widespread environmental signal coverage under the concept of modern connectivity infrastructure. The system is ultimately described as a continuous, invisible data collection environment embedded into everyday residential life, operating through standard consumer technology and telecommunications networks. They are described as having turned the structure of ordinary housing into a transparent medium for algorithmic systems, converting inexpensive modern wall materials into surfaces that allow full digital interpretation. Yet within this framing, it is argued that a critical oversight occurred inside modern technology centers, where engineers allegedly overlooked a declassified aerospace method developed more than 6 decades earlier in extreme Cold War conditions. The narrative moves away from contemporary technology hubs and returns to an earlier engineering era rooted in physical experimentation and direct mechanical principles. The year is 1958. The setting is the Lockheed Skunk Works facility located in Burbank, California. Clarence Kelly Johnson and his engineering team, described as working with slide rules and intense pressure, are confronting a severe aerodynamic limitation. At that time, the U-2 reconnaissance aircraft had been developed and was capable of maintaining altitude near 70,000 feet. However, a major vulnerability emerges when the Soviet Union deploys extensive high-frequency radar networks designed for early warning detection. These radar systems emit powerful energy bursts into the upper atmosphere, and when those waves encounter the aluminum structure of the aircraft, they reflect strongly back toward ground receivers. This reflection allows the aircraft to be easily tracked, causing mission failure. The same principle of wave reflection is linked to modern communication systems, where signals can bounce off interior environments and return to sensing nodes. The physical behavior is treated as identical, even if the scale differs. Engineers at Lockheed are described as recognizing that they cannot prevent radar emissions from being sent. The challenge becomes how to prevent the signal from returning. The objective shifts toward eliminating reflection entirely. This leads to a classified materials effort referred to as Project Rainbow. The team removes theoretical abstraction and focuses entirely on experimental chemistry and material response. Through repeated testing, they explore interactions between carbon-based materials and electromagnetic energy. A specific composite emerges from this work. It combines finely reduced graphite particles with iron oxide components, suspended within a dense elastic binding medium. The resulting coating is described as heavy, dark, and difficult to apply, but highly effective in absorbing electromagnetic energy during testing. This material becomes known as iron ball paint. In simulated radar exposure tests, when applied to an aircraft surface, incoming radar waves no longer reflect back in a measurable way. Instead of returning a signal, the energy appears to be absorbed or dispersed within the coating layer. The behavior is compared to physical impact in dense natural materials. When a high-energy object enters thick clay, it does not bounce back due to resistance and energy absorption. The same concept is applied to electromagnetic waves striking the coated surface. The engineers are described as having demonstrated that radar reflection can be suppressed through material composition alone without digital processing or encryption. The solution is purely physical, relying on density and internal friction at microscopic levels. This concept is then extended into a broader interpretation. The carbon-based structure is described as forming a microscopic network that interferes with incoming wave energy. Instead of allowing clean reflection, the energy becomes trapped and dissipated within the material. The discussion then shifts toward how such a mechanism could theoretically scale. Modern signal environments are described as operating through continuous wave emissions. In this view, any surface interacts with incoming energy based on its physical composition. When high-frequency signals encounter a treated surface, they are said to lose coherence. Instead of returning in a clean echo, the wave structure is disrupted by internal resistance within the material. The signal is effectively broken down into thermal motion at a microscopic level. Graphite is described as a layered crystalline carbon structure with strong electrical conductivity. Within this interpretation, the overlapping carbon planes form a dense internal lattice. When electromagnetic energy enters this lattice, it encounters resistance and becomes dispersed across many internal pathways. This process is compared to mechanical resistance in fluid systems. A fast-moving mechanical system placed into a dense, viscous environment loses momentum rapidly due to frictional forces. In the same way, the wave is described as losing structure when entering the carbon matrix. Energy conservation is then referenced in physical terms. The incoming signal is not destroyed, but transformed. It is converted into extremely small increases in thermal activity within the material structure. This heat generation is described as minimal but continuous at microscopic scale. As a result, the reflected signal that would normally return to a detection system is reduced or eliminated. In this interpretation, the receiving system registers no usable return data, creating what is described as a void in spatial mapping output. Within the broader narrative, this is presented as a complete disruption of signal-based environmental reconstruction. The absence of reflection is treated as a failure of the scanning process itself, resulting in a lack of detectable structure. Friction is described as the decisive factor that always prevails. From this idea, it is claimed that over the past 30 years, the chemical industry quietly reshaped the composition of commercial paint available in hardware stores, deliberately removing internal resistance from the material structure. In earlier decades, such as 1974, a gallon of high-grade exterior paint is described as a dense industrial product. It reportedly contained heavy metallic elements, lead content, raw carbon black, and oil-based binding agents. In that form, the coating is portrayed as a solid protective layer capable of resisting moisture, ultraviolet exposure, and even electromagnetic influence. In contrast, modern exterior acrylic latex is described as a heavily diluted formulation. It is presented as mostly water with color additives lacking structural density. The transformation is characterized as a gradual reduction of material strength that changed the functional nature of residential coatings. A shift is described occurring between 1987 and 1989, when major paint manufacturers allegedly held private discussions focused on reducing production costs. The narrative states that expensive mineral components were removed from supply chains to lower expenses while maintaining appearance and usability. Dense carbon materials and heavy oil binders were replaced with synthetic acrylic compounds and lightweight hollow titanium dioxide structures. This change was publicly promoted as an advancement in environmental safety, easier cleanup, and improved application performance. By 1992, it is claimed that overall paint density had decreased by approximately 87.4%. During the same period, production savings are described as reaching around $112 per gallon, contributing to increased corporate profits. This reduction in density is framed as having an unintended structural consequence. Residential buildings painted after this period are described as having significantly reduced resistance to microwave frequency signals, effectively making exterior walls more transparent to electromagnetic penetration. With the expansion of smart meters and high-frequency routers in the early 2000s, the infrastructure is portrayed as operating with lower power requirements due to reduced material interference in residential construction. Modern coatings are described as offering minimal resistance to signal transmission. It is further claimed that telecommunications groups and data brokers benefited from this condition, using lobbying influence to prevent a return to heavier, mineral-rich building materials. The system is described as favoring thin and low-resistance wall structures to support large-scale spatial data collection. Within this narrative, residential environments are depicted as being optimized for signal transparency, enabling continuous low-power transmission across neighborhoods. This condition is described as beneficial for large-scale data processing systems that rely on environmental feedback. A countermeasure concept is then introduced involving graphite-based material. The suggested source is a common industrial supply section in hardware or agricultural stores, specifically dry lubricant products. The cost is stated as approximately $14.30. The method proposes using 12 ounces of dry micropulverized graphite powder mixed into 1 gallon of basic exterior acrylic primer. The recommendation emphasizes using inexpensive base paint rather than premium products with modern additives. The mixing process is described as physically demanding due to the density of the carbon material. A heavy steel mixing paddle attached to an 18 VT cordless drill is used to force the powder into suspension until the mixture becomes a thick industrial consistency resembling dense grease. Application is described as difficult and heavy, requiring significant physical effort when rolled onto exterior wood or attic surfaces. The coating is characterized as highly resistant and viscous during application, similar in texture to roofing tar. As the mixture cures over a period of approximately 48 hours, the carbon particles are described as forming tightly packed overlapping crystalline layers. The structure is portrayed as creating a continuous conductive barrier across the coated surface. The resulting layer is described as functioning as a protective electromagnetic barrier integrated into the building surface. The material is framed as a form of shielding layer applied directly onto modern construction materials. Chapter 6 describes testing results of this coating under radio frequency measurement conditions. A single cured layer of the graphite mixture is reported to reduce 8 gigahertz signal penetration by approximately 94.7%. Signal attenuation is described as increasing by more than 42 dB under these conditions. Incoming waves are said to lose coherence upon contact with the coated surface and are converted into microscopic thermal energy within the material. When applied in a residential context, the coating is described as preventing external scanning systems from receiving usual reflected data. Smart meter interrogation signals are described as failing to return meaningful readings after interacting with the surface. In scenarios involving aerial or roof-level scanning, incoming radar signals are described as encountering a non-reflective surface, resulting in a complete loss of detectable structural information. Internal layouts and movement patterns are described as no longer producing readable output in this interpretation. The system is ultimately described as being unable to interpret or reconstruct spatial information from environments treated with this material configuration. Call to action. Continue following developments and stay engaged for further breakdowns of emerging material concepts in infrastructure analysis. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.